Thank you all for coming. I'm really happy to be here presenting at Google and to the engineers who helped make my research possible. I'm going to start by introducing a Googlewhack. By a show of hands, I saw that most of you have heard what a Googlewhack was and maybe even found one yourself. Basically, it's a search for a pair of words that returns exactly one hit in Google. As shown, when you do the search, it says results 1 of 1, and that's how you know it's a Googlewhack. Some of them are kind of funny, posted on Googlewhack.com. My favorite is protozoic spliff. But you'd imagine that two really common words would not be a Googlewhack because you'd have more than one hit. Where at the other side, two really, really rare words would have no hits at all, and so it wouldn't be a Googlewhack. So really, the numbers that are important are the number of Google hits for the first word and the number of Google hits for the second word. And I define them here with A and B. Also, I is another important number, which is the total number of pages on the Google index. This number used to be on the home page. R, I'm just defining to be the variable for the number of results for both words together, which for a Googlewhack is equal to 1. Now, if all...
Sorry, there's a way to spelling errors, of course.
Yes.
It's a very common word. And a spelling error but appears only once, and the whole thing is not so interesting any longer.
Yeah, actually someone pointed out that marshmallows here is spelled wrong. But in fact, if it was spelled right, it probably would not have been a Googlewhack. Now, if you can assume that all the pages on the index are approximately the same size, so the probability of a word appearing on a page is the same for any page in the index, then that probability will be equal to A, the number of hits for that word, divided by I, which is the total number of places where that word can be. To find the probability of both words appearing on a given page, you just multiply those two probabilities together, and then to get the number of expected results, you add all of the probabilities for each of the pages. And since there are I pages, you multiply it by I, which gives you R is equal to A times B over I. Now, for a Googlewhack, we set R is equal to 1. And to demonstrate it, I'm going to use a special log-log plot where the x value of all the points will be equal to A divided by B. That's the ratio of the number of hits for the first word versus the number of hits for the second word. And there'll be 2 points for each pair with the x value determined by that, and the y value will just be the height, the number of results, A and B. I took a few hundred Googlewhacks from the website, from what they call the Whack Stack, and it looks pretty good. A friend of mine, Eitan Bouquet, wrote a program that allowed me to automatically find all of the search results for the words individually, and we see that they do pretty much follow the 2 expected lines from the formula on the last slide, where I just plugged in the number taken from the Google homepage. Now, it looks great, but something is up. All the points seem to be lower than the theoretical lines, with less results than you'd expect them to have. But if we go back to our assumption that all pages are equal, that's not true because really there are a few pages that are really, really large and a lot of pages that are really, really small. Now, words are more likely to be found on the larger pages, and since both words A and B are both likely to be found on the same page, that means that you need rarer results, rarer words for a Googlewhack, and so all the points are actually lower than you'd expect them to be. Now, to refine the model, we're going to need to know the distribution of page sizes on the internet. Now, lucky for us, Adamic and Huberman have studied this, and they've shown through a number of studies that the size of the nth largest page, the size of the pages follows a Zipf law, where the nth largest page will be proportional to 1 over n to the alpha, where alpha for the internet is equal to 1. So if we rank the pages on Google from 1 all the way to capital I, and apply the Zipf law, we see that the number of pages, the number of words per page on the ith page will be proportional to 1 over I to the alpha. But we need to know the number of unique words because it doesn't matter how many total words are on the page, but the number of different ones if we want to know the probability of a word appearing on the page. And so we use Heaps law, which is a linguistic law, which says that the number of unique words in a text of size n will be proportional to n to the beta, where beta is another constant, normally between 0.4 and 0.6 for the English language. Merging those two together, we can find that the number of unique words on the ith largest page will be proportional to 1 over I to the alpha times beta, where alpha is the Zipf coefficient and beta is the Heaps law coefficient. Now, that is only if there's, let's say, one hit on the index. Then, if there's one hit over all the pages, then the probability will be proportional to the number of unique words, or equal to k over I to the alpha beta for some k. Now, if we sum all the probabilities, the same way we did for the basic model, then it should equal 1 in this case. And that allows us, if we approximate that sum from 1 to I with an integral, then we can actually come up with a formula that will be equal to k, which will give us this formula for the exact probability of if there's one hit of a hit landing on the ith page, where alpha is again the Zipf law coefficient and beta is the Heaps law coefficient. But we need to know the probability if there's more than one hit on the page. Turns out that if you add more hits, you just simply, it goes proportionally, the probability. So the probability if there are a hits on the ith, the probability of a hit being on the ith page if there are a hits is approximately equal to a times the probability if there was just one hit on the index. Now, to demonstrate that, though, I made a computational model where, for an internet of 100 pages, and I randomly did it a few times and found the exact probabilities of hits landing on the ith page, where, again, the page sizes, or the probability distribution, is given by that coefficient, alpha times beta is 0.52, which later we find is actually the case for the internet. And so we see that as long as the number of results is much smaller than the total number of pages on the index, then these linear approximation lines work well. Now, actually the lines are starting with the blue line, which is the probability for a word landing on the largest page, which goes up quickly as the number of results increases, and the purple line is for the smallest page, which goes up slowly only at the end when you've almost filled up your entire index does it approach the probability of 1. But again, the important thing is that as long as a is much smaller than I, these lines approximate the curves accurately. And for the case of the Googlewhacks, all the results used are much, much smaller than, over 100 times smaller than the total size of the index. And so we're okay using this approximation, which we now use to find the probability of a given word being of two words being found on a given page I. And it's equal to a times b times that formula there with the index I being the ith page, which we then, if we want to find the total number of results for both words together, the same way we sum over all the index from the first page to the last page, and we approximate that sum with an integral, which gives us an exact formula for the number of results in terms of a, b, capital I, and alpha beta again. Now, if we look at this, though, since everything in that to the right of a times b is a constant, it's really very similar to the basic model, the only difference being that constant. And so we can lump it all together and define it. I call it the effective index size, or IEFF2, 2 being because it's the effective index size for a pair of words. And make that all, just call it that, and it looks the same, which allows us to graph it. Before we graph it, a times b for a given number of results, in this case 1, should be equal. But since it's really, these are random things we're dealing with in probabilities, we should expect some kind of distribution for the results. And since it's a times b, which is multiplying two random numbers, we'll expect a log normal distribution, which indeed it has. This is a histogram of all the different numbers of a times b. And we see that there's a sharp peak there, which we can find by taking the geometric mean. So with the geometric mean of a times b, we can plug it into our formula for the number of results. And of course, setting r is equal to 1, because all of those points had one result. We're going to take off the Google homepage as around 8 billion. And the Zipf law we're going to take from Adamic and Huberman and set that equal to 1. So the one that's left is beta, which we can solve computationally for and come up with beta is equal to 0.52, which fits nicely between 0.4 and 0.6, as other results have shown. Now, what's really neat about this is that previous studies used only about 20,000 pages, where this one actually used the entire Google index of around 8 billion at the time, when in practically a fraction of the time used for the normal methods. But of course, that's not counting the hundreds of people that spent hours trying to find the Googlewhacks in the first place. But it's still faster, at least for me. If we go back to this graph, we can simply, since the model is really the same with only that constant being different, we can plug in the effective index size for I, which now shows that the theoretical lines lie right in the middle of all the points. So this is a good result. But we're not actually limited to Googlewhacks because R in the formula works for any number of results. And so I searched for random word pairs. In this case, the y-axis is the number of results for both words together, and the x-axis is the product of the individual word results. That's A times B, which for a given number of results should be constant. And it should follow the black dashed line. And in fact, if you look at the cloud of points, it pretty much does. And it's even clearer when you look at the geometric mean. That's the red line taking a geometric mean for any given result R. We see that red line follows the theoretical line rather closely. But the green points are points that they're word pairs that I chose by hand because I thought that they were related in some way. And so you'd expect them to have more results than it would just based on a random process. And in fact, they do. You see that all the green points are above the black dashed line, showing that they have more results than expected just from the model. To quantify that, I defined the strength of associativity to be equal to the log base 10 of the actual number of results divided by the expected number. And for this example, Smashing Pumpkins has a value of 2, meaning that rock band has so many fans that their number of Google hits for those 2 words is over 100 times what you would expect it to be. Whereas Search Protector has a value of 1, meaning it's about 10 times more likely to show up than you would expect it to. Grand Slam is an example where I thought that there was something, a good relation between them, but really just the random process was much more than what I had in my mind, and so it only has a value of 0.5. Now, there's a value for the effective index size in my formulas, but of course that grows as the internet goes. So on the next plots, I show an experiment where I'm just going to keep the geometric mean line. So these lines are the geometric means for a search of the same points, actually. One in August 2005, when the index was around 8 billion. And the other graph is from April 2006 with the same words, but then the Google index was known to be about 25 billion. And we see that the theoretical dashed lines match well, where the only difference was plugging in that value, the known value, for the index size. Now, at some point, though, Yahoo was claiming that they had a larger index than Google. I'm not sure what happened, but in the end, Google took that number. You guys took it off your homepage. But it's still in my model, and so with the help of another friend, Virgil Griffith, I got identical data for Yahoo, compared them. This is 2 experiments at the same time with the same words, with the search engine Yahoo and Google, plotting the number of results versus the product of individual results. And that dashed line, I chose picking an effective index size so that it matched the data, which you can then extrapolate back to find the actual index size of being around 28 billion for both Yahoo and Google. So in the end, they pretty much have the same index size. Now, we're not limited to word pairs either by the model. In fact, we can extend it quite easily to word triplets by simply adding a third word, multiplying that probability in. That is, the third word has a C. The number of results for the third word is C. And you sum over the index again and come up with A times B times C over I squared will be equal to the number of results. That's for a 3-word search. But this is the basic model. To go to the refined model, you might have guessed already that you simply plug in an effective index size, 3, into the basic model and to get the result. But the math behind it is made easier because we already defined all our parameters before. We already have the numbers in, so it's just calculating an actual integral, and we come up with this value for the effective index size. And it actually fits the data nicely that all the points lie around the theoretical line, which is good because even though we calibrated it for the basic model, with this, there's no extra calibration. This result came straight out from the formulas. You may be wondering, though, why the points are, let's say, they kind of seem spread around the line. They're not exactly on it. So we can ask the same question also for the word pairs. Maybe the mathematical model has some description which could explain why the spread is so large, and also why it seems to be shifted over to the left with less points to the right of the theoretical line. Now to do that, we need to find the exact probabilities. So we're going to go back to the basic model one more time, and say that the probability I'm defining as P of R, the number of results, comma A, comma B, comma I is again the total index size. And the basic model again is that all pages are equal. So the probability of a word appearing on a given page will be the same. It doesn't matter which page you choose. So the probability of a hit being on a page will be equal to the total number of ways to combinatorically arrange R hits over I pages, divided by the total number of ways to arrange both hits A and B, scatter them across the I pages. And so you can solve for that, and you get this big formula here. But now to go to the more refined model, we simply plug in the effective index size for word pairs into this exact formula for the probability with the basic model. But to verify that, I use the computational model again, this time with an index size, a fake internet of 500 pages. And alpha beta is, again, that's the distribution of page sizes, will be 0.52. Which then gives us an effective index size of 277 simply by plugging it into the formula. And this graph is an example where the number of hits for both words were both 40 out of 500 pages. So the blue line is a discrete probability density function. That is, it shows the probability of getting exactly that number of hits in this case with A times B equaling 40. So for example, the probability of getting 5 hits is approximately 0.2, while the probability of getting 2 hits is about 0.05. Now the dashed line is the probability just plugging in the effective index size into the exact formula for the probability from the previous slide. And it matches quite well. And as you lower A and B, it eventually matches almost exactly. But what's actually important is the way that it differs is not in the width of the peak, which is what we're interested in. We want to explain the spread. So if that peak was really wide, then it would explain the spread. But in fact, it's not. If we plot now the exact probabilities, overlay it on the same plot for the word pairs, here those lines represent lines of equal probability, where you have a high probability over here, and it gets less and less as you go further out. And actually, it doesn't look bad because the general shape of that probability contour closely matches the general shape of all the points spread out. But actually, it doesn't explain it entirely because the area that's white has a probability less than 10 to the minus 15. And in fact, that means that there's a really high probability of it lying within that spread. Whereas the points, as we can see, they're not all in the spread. They're kind of still spread out. To emphasize that point, I picked an example here that has a 99.99% probability that the results will be between 600 and 800. While if you put those words into a Google search, then you'll get only 12. And that's actually not uncommon, that you'll have a really high probability of results being somewhere, and they're somewhere completely different. So to explain this, we actually have to go back to our assumption that the number of Google hits is actually the number of pages that those words appear on. Now, a search for a search for miserable failure became famous when basically it returned the webpage for George Bush's biography on the whitehouse.gov website. Obviously, the words miserable or failure were found nowhere on that page, but Google still counted it as a result and counts it as a number. So there may be other reasons, which perhaps you guys can maybe tell me some reasons for, why the number of results may be different. Also, I'm assuming it's mainly because, it's more important to have relevant hits than actually display the exact number of words that appear on a page. But I can still, even though I can't explain why, I can still come up with a value for the magnitude of these effects, which will then allow me to explain the spread in the model. So one example is the order of the search terms, which actually changes it a lot, even though clearly the actual pages that both the words appear on doesn't change depending on the order that you put the words into. But in this case, the number of results is off by 10 times. So in doing searches like this, I found that on average, just switching the word pairs order will get results off by 1.5 times, which isn't enough yet to explain the spread, but this is a case where that's definitely the reason for it. Also, another way to come up with a measure Here, A, bracket A, is defined as the number of pages with word A. Brackets A minus B is the number of pages with word A, but without word B, which you can find simply by plugging in the minus character before B in the Google search. We'll give you that number. And bracket A space B is the number of pages with both words A and B. You can come up with this arithmetic formula where the number of pages with A but without B, plus the number of pages of B but without A, plus the number of pages with both A and B will be equal to the number of pages with A plus the number of pages with B plus the number of pages with, minus the number of pages with both A and B, which you can rearrange to this formula here, which I then tested for a few results, checking both sides of this equal sign, and found that they were off by, on average, 10 to the over 100 times off, and sometimes as much as 10 to the 5.6. So changes of this magnitude are definitely enough to explain all the spread we see in all the plots. To conclude, I developed a model to predict the number of results that should be returned by a pair of words entered in any internet search engine, based on the number of results when you search for the words individually. I used the data from Googlewhacks to calculate the Heaps law parameter beta for over 8 billion pages when previous studies used far less, and in a very short amount of time. I demonstrated the robustness of the model with word triplets and with different sizes of the Google index. And I also used it to compare Yahoo and Google to find that they both have an index size that is about the same, regardless of whatever claims. I quantified a potential cause for the widespread of results when the model didn't explain it alone. I also described a fast method for quantifying the value strength of associativity between any two words in a pair. Future work might look into whether the Zipf and Heaps law parameters will change depending with time as the internet grows. Also, someone might be able to use Google's advanced search options, which allows you to specify a particular domain, to maybe investigate other languages, find the Heaps law coefficient for other languages, or for particular countries. Also, someone could make a more refined model with better understanding of where the differences from this model come, which would give you more accurate values for all the parameters as well as strength of associativity. Now I'm going to end by mentioning some potential uses for this value, which I think might be interesting. First of all, it's very quick. To actually come up with your value only takes 3 Google searches, which is fractions of a second, and it can be automated for a large list of words in a very short amount of time. So one thing you could do is maybe with AdWords or search results, you could link an ad to a page not by words that actually appear on that page, but maybe words that have a strong association between 2 words, even if they're not both on the same page. Also, anomalies, that is, values of really, really high strength of associativity or really, really low, might be able to find, let's say, a bug in the number of search results returned. Or if it's not a bug, then I'll call it an interesting discovery. So thanks again for listening. And if you have any questions.
So the big black box here is Google, right?
Okay.
So
Yep.
you said that other studies use 20,000 pages.
Mm-hmm.
If you had expanded that 20,000 page study with your own, defined by yourself, search algorithm, would the results be?
Yeah, probably if you could, let's say, use 20,000 pages. Oh, do you mean use 20,000 pages?
8 billion pages to use your own search algorithm.
Oh, well, if you could in any way find definite exact results, rather than, there's some, I think, discrepancies between the number of pages and the number of results displayed. So if you could come up with your own search algorithm that would actually, it would take away all the fancy tricks that allow for better searches and simply return the number of pages only, then yeah, you would probably get more accurate results. We would hope so. The spread for Yahoo was comparable to that of Google, so it's a good question. They pretty much, the reason I used the geometric mean was because if you look at them both overlaid, you'll just see a mess of points. And they're pretty much equivalent. So that's a good question.
Otherwise, you just measure the effective English index size for English page.
Yes, that's a very good point. So I have to assume here that most of the pages are in fact English, and the only way that may not be true, especially today, and the only way that I have to support the model is basically if that were the case, then the word triplet results would be off, and the Heaps law parameter would also be off. And as the index grew, of course, that might have other effects. So the fact that the model worked for those cases shows that it's not just the English pages or the English page size. Any questions? Yep. Yeah, so I suppose if it's way off, like if the search engine is claiming that they have, let's say, I don't know, double or 10 times more than the model shows, then perhaps, I mean, they could be lying, or they could just have a lot of pages that are blanks, you know, like they may be actual pages, which they're counting as pages, but they don't have any words on them. So I don't want to accuse anyone of lying, especially when certain cases, some of the results, they're not 100% that they count as pages. They're real pages with both the words on them. So I'm going to hesitate to accuse anyone of lying, but I suppose if you're into that, you could. I don't think so, because it's just based on the number of hits. So, and some of them are actually quite large, because as the other one of the graphs showed, this one, as you get to here, that's actually a very common word that's paired with a very rare word. So it's not always very rare words.
Googlewhacks with both different languages. So there's some pages written in multiple languages.
Mm-hmm.
In those pages, you have a skewed distribution of language. For example, I suppose many Chinese pages will have the word home there. Because it's a common computer term.
Yeah.
So you may fall if you don't pay attention, because the word distribution, because we're using common terms, common technology, the word distribution might not be the same as if you read, let's say, a novel. In computers, certain words are very common.
Mm-hmm.
That might, I don't know if it might change your gross calculation, but it might change particular pairs.
Yeah.
Your entire result.
That's a good point. And the fact that the geometric mean line, if you remember, it squiggles around the black theoretical line, that could definitely be a good explanation for it. Maybe as it gets more, as you have higher results, because it's, let's say, including pages from other languages. Maybe that's a good point. Yep. I think as long as the words are scattered randomly on those spam pages, then it's okay. So the results should stay the same as long as that's the case.
When you did your computation studies,
Uh-huh.
you were generating a fake internet of 100 pages.
Mm-hmm.
Were you generating it using your discovered Heaps law coefficient?
Yeah. So basically what it was is 100 pages, and there was a given probability that a hit would appear on a page based on the Heaps law coefficient that was discovered. And then what I would do is basically just scatter A hits randomly across the pages, scatter B hits, and then see, or well, actually in those graphs, so it's just scatter A hits, and then find out the probability, do that like a million times, and then find the probability of one of those hits appearing on the biggest page all the way down to the smallest page. Did that answer the question?
Okay,
So I used that same distribution, even though it was for a smaller size index.
okay, but then, so you just reproduced the product of the Zipf law and stuff.
Yeah, yeah. Yeah. All I care about is that the probability of a word appearing on the page is given by that distribution. That's what I care. Questions? Yep. I can give them to you if you'd like. Oh, it will be on YouTube.
Yeah, but that's not the same as having the slide. I can click the slide visually.
Yeah. Sure, if you'd like them. Yeah, I can give you my email later, or it's up there. All right, I guess thanks for listening.